problem that we are going to solve using the dynamic programming approach is the longest common subsequence. So first of all, we have to understand what is longest common subsequence. See, such kind of applications exist when we are going for the DNA analysis. So like we know we all are facing the problem of COVID, and the people, all the scientists across the world, they are trying to understand the characteristics of the COVID virus. So when they are understanding the COVID virus, basically they are trying to understand the DNA. So it's not a DNA, basically it's an RNA sequence of the virus that exists. So what is there in that RNA sequence? We can say they are certain, you can say, sequence of symbols that can be represented, you can say. So that DNA, so DNA is nothing but a combination of two RNA strands. So this DNA consists of various, you can say, genes. So these genes, they are characterized by some characters like A, C, G, T, and these are in a certain sequence. So understanding the sequence and identifying that particular subsequences. So these different kinds of applications are there in the field of biotechnology. So what we are trying to understand when we have to see the subsequence, here when we are referring to the subsequence, that doesn't mean that all these characters, they should be consecutive to each other. The only thing that we require is in this particular, like S is a sequence of characters of ACGT. And now when we are looking for a subsequence, then we are just looking for that if we have first character A, then we may be missing certain characters, and there is a character C, right? And then C is followed by G at some point in the sequence, and then G is also followed by T at some point in the sequence. So that means we are talking about a sequence. Sequence doesn't mean that all these characters, they exist consecutive to each other, right? But they are one after the another only, that we are calling as a sequence over here. So when we are given two such sequences, let us say we have one sequence of X, another sequence of Y, then our goal is to find out such longest common subsequence that exists in both the sequences, that is X as well as Y. So here you can see that when we are looking for this in the S, so in the S, Z is equal to CGTC is the subsequence of X, that is ACGC So here you can see where is C. So when we have C, right? So we have C, yes, that is there in the X. Then we have, after C we have a G, yes, it is there, followed by this. Then we have G is followed by T. So G is followed by T, but that is not consecutive, that is after C. So it is at some point, but it is there, that T is followed by C. So similarly over here, C is coming after T. There may be any number of characters in between, but it is followed by C. So we are looking for a subsequence like this. So here you can say we have to find out the longest subsequence, such kind of a sequence which exists in a particular range of characters which are available to us. So here you can see, so the common subsequence Z of X and Y is a subsequence of X and also a subsequence of Y. So here you can see when we say Z is equal to CGA is a common subsequence of both X as well as Y. So if we compare, we have both C. C is there in the X as well as in the Y. Then C is followed by G. C is followed by G in X as well as in Y. Then G is followed by A. G is followed by A in both X as well as Y. So similarly, if you want to extend, let us say if I say ACG is a subsequence of X and Y. So do we agree to that? Let us see. So if I consider A, it is there in the X. So let us say at some point A is there in the Y. So we will have to see, we cannot go back. We have to understand. So we cannot go back. If we are going forward, there should not be any crossing, right? So let us say after A, G is coming, right? After A, C is coming. Yes, it is followed by A in both x well as well as in y. So we have AC here also, we have AC in y also. Then we see G. G is there in the x, but G is not there after the C. It is at the back. So you can say if we will make an arrow, and then that arrow will go back and it is going to create some kind of crisscross. So backward is not possible. Forward is there. If both are backward, then it is fine. So that means we have to see there is no crisscross. So G should be followed by C in the same order, in the same direction, right? So that means ACG is not a common subsequence of X and Y, but AC is a common subsequence of both A and Y. So similarly, we have to find out. So we have to find out a strategy such that we are able to find out the longest common subsequence. So let us say, how do we define that? Given we have X as a sequence of certain characters or some numbers, then similarly Y is also a sequence of characters, and our goal or our objective is to find the longest common subsequence. So if we consider the brute force approach, what we will do? We will find out all possible subsequences. So you can understand the number of subsequences which are required to be computed, and then we say it's going to take. So if we take the value of MC, the problem of the brute force strategy is with the increase in the value of M, so the computation becomes exponential. So if M is small, M is 2, 3, 4, 5, you see, we can do it. But if M becomes 100, then it becomes very complex to compute the longest common subsequence using the brute force strategy. So in order to get rid of this kind of a problem, we go for the dynamic programming approach. So in the dynamic programming approach, we know that it is based on the principle of optimalities. That means if we are able to find if the solutions to the substructures they are optimal, then we can find out the optimal structure for the problem. So we can find out the optimal solution to the problem. So here let us consider X is a sequence, then Y is also another sequence, then Z is another sequence, and we have to, so you can say Z is the longest common subsequence of both X and Y. So we have certain conditions. Let us say if Xm is equal to Yn, so if both are same, then Z is also having the same subsequence, then Zk minus 1 is the LCS of Xm minus 1 and Yn minus 1. If Xm is equal to Yn, not equal to Yn, right? That means if we are comparing the characters which are not same at any point, it means there is a possibility that we have seen that in this particular example, both X and Y, so A is not equal to C, C is not equal to T. Like at some point, C in the third point, G is equal to G, right? So here Xn is equal to Yn. So we are comparing these characters at these positions. If Xm is not equal to Yn, then Z of K is not equal to Xm, implies Z is the longest common subsequence of Xm minus 1 and Yn. Similarly, if Xm is not equal to Yn, so and Zk is not equal to Yn. So here you can say in the previous condition remains same, but in the second condition there is change. That will imply that Z is the longest common sequence of Xm and Yn minus 1, that changes. So similarly, we are going to find out the longest common subsequence for the particular problem. So what does this particular theorem says? If we compile both all the conditions, it says that if Xm is equal to Yn, then find the longest common subsequence of Xm minus 1 and Xn minus 1. So that means if they are same, then we just have to find out the longest common sequence of both, and then we can just append the Xm. And if Xm is not equal to Yn, then we have to find out the longest common sequence of Xm minus 1 and Yn, and similarly for the third case, whichever and we take, this is a longer. So for overlapping substructures, we can say now from here we can say we are trying to find out what is overlapping over here is that for both the cases, for both the Xm minus 1 and Yn, and LCS of Xm and Yn minus 1, we will need to have the Xm minus 1 and Yn minus 1. From here you can see if we need Yn, for that we also need Yn minus 1, and for the other one also we need that. So what is the common overlapping substructure that we have to identify? Because we have to see the dynamic programming approach is a bottom-up approach. That means we will first find out the solutions to the sub problems, and then finally these will be used for finding the solutions to the main problem. So that's why we are finding out the overlapping substructures. So that means if we are able to find out the xn minus 1 and yn minus 1, we can also compute the xn minus 1 yn and the LCS of xn and yn minus 1. So let us start doing that. As we know, for solving any kind of problem using the dynamic programming approach, we are creating a table. So what we are going to do is we are going to create a table over here, that is Cij. Cij is length of longest common subsequence of xi and yj. So how we will be filling up this table? If I is equal to 0 or j is equal to 0. In both the cases, what we are going to do is value equal to 0. If I and j, they are greater than 0 and xi is equal to y, that means if x is one sequence, y is another sequence, and we have to find out a common subsequence. So if the value of whatever value is there, that means a particular character that is there in the x and the particular character that is there in the y, if both are same. So in that case, what we are going to do? See, we are going to take the value of the diagonal, that is I minus 1. I minus 1 will lead to previous row and j minus 1 will lead to the previous column. That means it will become the diagonal cell. So the diagonal cell plus 1, whatever is the value in the diagonal cell, we will be adding 1 to that, and we will fill this particular Cij value. If xi is not equal to yj, that means if the characters in the corresponding characters in the both the sequences, they are not same. So in that case we are going to take the maximum of the row value as well as the column value. Here you can say the corresponding row. So we have just decreased the value of the row, and in the second case we have decreased the value of the column. So we will compare them, and then on the result of whatever value is maximum, we will fill that value in the Cij. So computing the length. After that, what we will do, we are going to compute. We have filled that particular table using this particular formula. Then Cmn will be the answer to the length of the sequence. Then we have to find out, as we did it previously. So once we have filled the table, we have found out that this is the length. Length is, let's say the maximum length is 2. Then what are the two characters we have to identify that form that particular sequence? So, and in what order? So we are going to have v is equal to 1 to m, where Vij points to a table entry corresponding to the optimal sub-problem solution. So that means from the table entries, we will find out, as we did earlier. So we will see, when we are filling the table, we move from top to down. And then when we have to trace back all the elements, we're going to form the longest subsequence. Then we will be moving from bottom to top. And then see, as we move upwards, we are going to see from where that particular value originated, and then we will be taking that corresponding character or element. So we will be moving backwards, and we will be taking up only the diagonal elements. So let us say that we have these two. I'm taking a small example so that we are able to understand it very precisely. So let us say A and B are the two sequences. From these two sequences, we have to find out the longest common subsequence. So here we can see from here we can clearly see that the longest common subsequence is BD only, because in both the sequences the B is followed by D. But how do we find this subsequence using that programming approach? So in the pseudocode, what we can see is if AI is equal to Bj, that we have seen. So if AI is equal to, so that one where we have written Cij is equal to 0, that has been omitted over here. We know the first row and the first column, that is going to be zeros, and then we are starting from the first position only. So here when we say if AI is equal to Bj, then let us compare. If AI is equal to Bj, that means A of 1 is equal to B of 1. So they are not same. So this condition is not met. They are not same. We will go to the else position. Then in the else position, how we are going to fill this particular table? So this is 1 1 only. This is equal to maximum of 0 1 and comma 1. So what is a maximum value? So we, as I told you, that we initially fill the all the zeros. So after that, so if we see the value of 1 1, so 1 1 is also 0, because here you can see what is maximum of LCS 0j. What is 0 1? So 0 1 is 0 and 1 0 is also 0. So the maximum of both is 0. So that's why we have placed at the your LCS 1 1 is equal to 0. So let's move next now. As we move further, so we are moving from 1 to 2. So here we see, so as we are moving further from 1 to 2, so 1 to 2, that means AI is equal to BI. So the first condition is met. So I is equal to 1, B is equal to B of I, J is equal to 2. So as we move further, so their values are same, because at both the places B and B is there. B is there in the second position and the second sequence, and at the first position in the first sequence. Since they are same, so if the condition is met, in that case, we have to fill the table like this. This is equal to 1 plus diagonal element. So 1 plus diagonal element, so the position was 1, 2. In this position, diagonal element is 0, 1, right? So the diagonal element is 0. So we say that 0 plus 1 is 1. That's why in LCS 1, 2, the value that is coming up is 1. So as we move next, so we say 1, 3, right? So A I is 1 and B of J is 3. If it is 3, they are again not equal. But they are not equal, and their value, we say we have to go to the previous value of previous row and previous column. So that becomes 0 and 1. The maximum of 0 and 1 is 1. So similarly, as we move further, since B is not equal to D, so the maximum of the cell value previous column and the previous row, that is 0 and 1, that becomes 1. So similarly, we are going to fill these values. So and finally, we are able to get this particular table. So from this particular table, now the question, this particular table, how do we find out what is the length? So the maximum length of is the last value, because we are here we are D, the D value of both, that means 2 by 4. So here we say why we are taking this max, because this length is covering all the subsequences. So the maximum value that we are able to get over here is 2. So that means this is the length of the common subsequence. Now we know what is the length of the common subsequence, but how do we find out what are the two characters, whether it should be AB, it should be BC, or it should be BD? So we have to see because when you are going to implement this particular solution, in that case you will be not having, you can't see, the program cannot see, we have to understand the logic. So from understanding logic, we say we will see the diagonal elements. So because this 2 value we received from the diagonal only. So here you can see if AI is equal to BJ, both were D. So we did 1 plus LCI I minus 1, J minus 1. So that means the first element that we are going to consider is 2, and 2 is 2 gives us the character D, and then we move diagonally. So we got it diagonally. So here we say 1. So if we see the diagonal element, it is 0. That means it is not received from here. So we move from to the left side. So here you can see arrows. See here you from there you see the arrows as we move diagonally to 1. 1 is not received from the 0th position. It was not received from the diagonal element. It was received from the previous element. Then we see this 1 is received from the previous element. So its diagonal element, previous element is 0. That means it was received by adding 1 to it. So that means the two elements that we are going to consider, which form the common subsequence, is that is B and D. So this is how we solve the problem using the dynamic programming for finding out the longest common subsequence. So here you can see, here when you see the Corman book, this is how it has been explained. Since it was a bigger example, so I have made it try to make it clear using a smaller example so that you understand the concept clearly. So you can go through this. The same thing has been written over here in the form of the code, and when you're going to implement, the same logic has been implemented over here. So here you can see if xi to yi, then Cij is equal to Ci minus 1, Ji minus 1 plus 1. So here you can see this is the diagonal element value. And else if what we are going to do in the other case, Ci minus 1 comma j is greater than. So we are taking the maximum of, we cannot write max of this over here. So whichever value is maximum, again accordingly the values have been assigned to that. Such values have been assigned to the cell position in this particular matrix. So this is how you are going to construct the longest common subsequence using this dynamic programming approach. Now we move on to see if you have any doubts. You